Today we're going to be talking about the curl and how it's used for Maxwell's equations. So let's just jump right into it. Here we go. So we have this equation. Whose equation is this? Ampere's law? The integral of B dot dl, and that's equal to mu naught I enclosed plus what is it? Mu naught epsilon naught d of the electric field dt. So this is the current, and this term right here we call the displacement current. Now this is the integral form. We want to write it in the differential form, and that's going to be written as the del operator cross the magnetic field, is equal to, now this term becomes mu naught times the current density, not I anymore, plus mu naught epsilon naught. And instead of this term right here, we're going to get the change in the electric field as a function of time. I think I wrote that right. So going from here to here. Now, when do we use which equation? If we're using the first equation right here, it's typically for just a wire, let's say with current I going this way, and we're going to have some magnetic field going around it, like that. So there's current going that way, and then there's a magnetic field that's produced that way. And so we use the first equation for that. And I should mention that what I'm talking about when I do this is just the first term of the integral. So we don't really care about this. We'll look at this term later on in the lecture, but we're only interested in this part right here. So when I have a wire with current going through there, I can create a magnetic field that goes around it. I use this equation right here, the integral form. When would I use this equation right here is when I'm not looking at the wire from the outside, but I'm actually inside the wire. So when we go inside the wire, and there's current going through here in some direction, I. Okay, so that's the direction of the current. We can figure out what the magnetic field like around some loop is inside. So what color? We'll use blue. So instead of looking at the entire radius, we make an Amperian loop here. And we know that the magnetic field in this loop has to be going some distance like that. And this is some distance, little r. Okay, so that's the magnetic field inside of a wire. And that's when we use this equation right here. The differential form is equal to that term right there. So this right here is called the curl of B. The curl of B. What does that mean? Now there is a mathematical way of interpreting the curl, and then there's the physics way of interpreting the curl. So the way I see it is curl, this thing right here, I think of curl as equaling the circulation divided by the area. So that's my definition. Well, it's not my definition. It's actually Maxwell's definition. So you remember that this was Ampere's equation right here. This term right here was actually brought in by Maxwell to give you the complete equation. So Maxwell came up with this idea right here. He came up with the curl del cross B, and in his mind, it meant the circulation divided by the area. Well, since I'm throwing terms at you, what do I mean by the circulation of B? What do I mean by the circulation right here? What I mean is that if you have your wire here and you create a loop here, B is going to, there's going to be a little magnetic field that's going to loop around this distance away from the wire. So it's circulating around here. And the circulation is going to be given by how strong B is multiplied by how long it's going around, the distance that it's going to go around, which would be 2 pi r for a loop. And the area is given by pi r squared. Or we'll just leave it as pi for now. So it's going to be this over area. Okay? So that's what the curl of, in this case, would be the curl of B. This and this mean the same thing. Okay, so if that's what the curl of B means, it means the circulation divided by the area. Let's actually see if the equation works out. So the circulation over this, so we have this thing is equal to this, which is equal to this. So these two have to be equal. If this is equal to that, and this is equal to that, then this and this have to be equal, and we end up with mu naught J is equal to the circulation R divided by the area. Well, is that true? Okay. Well, J is the current density. The current density is just I over A. So we could rewrite this as mu naught I divided by the area. And so from here, you can see that the areas will cancel out, and you get the equation for Ampere's loop. It's B times 2 pi r is equal to mu naught I. That's what we do right here. We take the B out, and then when we take the integral of this, it becomes 2 pi r. And on the other side, we get mu naught times I enclosed. So this works out to be that. All right? So by definition, how is this and this related then? Like this. We can say that the integral of B dot dl, if you divide it by the area, that's going to equal the del product, the cross product. So the enclosed loop divided by the cross-sectional area is going to equal the curl. And people don't see that connection here, but that's what the connection is. All you're doing is you're taking this and dividing it by the cross-sectional area, you get the curl. Okay? Let's keep going. Cool. Now, let's talk about the curl in terms of mathematics here, just really quickly. So the way I envision curl when we're looking at like vector fields is you could think of like a water. Let's say this is downstream going that way and there's water, and you can represent the waters as vector fields. So velocity vector fields. So you got here, 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 here. Okay, so I've got this uniform vector field that's all going in that direction with the same size. Now, if I take a log, let's say here's my log right here, this pen, and I just drop it right here and I let it go, well, because the vector here, here, and here are all the same size, they're going to push on this log with the same amount, right? So it's going to move straight. So here, in this example right here, we don't have any curl going on here, and we don't have any divergence either, because the strength of this and the strength of this are equal. Now, what happens if I were to increase the size of each of those arrows? So let's say over here, like you go down a little waterfall and you increase the flow rate or something, I don't know, and then it gets even bigger like that. So if that was the vector fields, how would we write this? This would be something like y equals, this vector would be, what could this vector represent? It could be y squared in the I hat direction. So what this is saying is that as you, am I saying that right? No. It would be x squared in the y hat direction. X squared in the y hat direction. So as you move in the x direction here, as you move in the x direction, as you move in the x direction, you are going to increase in terms of that, but as you move up in the y direction, you don't get anything. I think that's the equation there. I don't know. Whatever, that's not the point here. The point is this. We take this log and we put it right here and we let it go again. Well, the point here, here, and here is exactly still the same, so it's still going to speed up. No sort of rotation going on here. So everything is still pretty fine and dandy when you do that. There is divergence though, because over here, the input vector fields and the output vector fields are different, right? So it's going to increase, it's going to accelerate. Okay, what if we had this? What if we had a situation like this? Where you had very large rates of water flow going this way, but you had smaller rates of flow going this way and this way. Now, if I took a tiny object, let's say I took a tiny object and I placed it right here. If I took a tiny little stick and I dropped it right there, what would happen? The water here is flowing much faster than the water here. So after some time, this log is going to turn like that because it's moving faster here than over here. I mean, it's still moving forward, but it's going to move forward much greater at the top than at the bottom. And what you could see is that if we continue this, this log is going to rotate. And that's where you get curl. That's the idea of curl. So when you move I don't know how to actually say this. So the perpendicular to the direction you're moving is changing, whereas with the dot product or the divergence, it's the vector that you're moving in the direction with. And I guess that sort of makes sense because when we do like a dot product of something, A cross B, when we do the cross product of something, the magnitude of it is going to be AB sine theta, which is the perpendicular component. And if we take the dot product, I don't even need the magnitude there, I just wrote there. It's going to be when you're dealing with vectors that are in that direction, okay? So we're looking at, you're moving this way, but we're interested in how it's changing perpendicular to it. So that's what will happen there. Now, something of important noted is this. You remember when I talked about divergence, we had three different ideas with divergence. If I did divergence, ooh, that's not a triangle. If I did the divergence like this, and I said it was greater than 0, that would imply that the field going in has to be less than the field going out. And we did the same thing with less than and equal to. We did something similar. What about when you have something like this? This cross some vector is greater than 0. What does that imply when the cross product of some vector is greater than 0? What that means is that you are rotating counterclockwise. So if I put the log over here, right, then this part of the log would move faster than this part right here, and it's going to rotate counterclockwise. So when you have a cross product or the curl being greater than 0, that implies that you are rotating in a counterclockwise direction. Whereas if you had it less than 0, that would be somewhere right here. So somewhere right here, the curl along this side of the field line would be less than 0 because you are rotating in a clockwise direction. And finally, somewhere right in the middle would be where the curl is equal to 0, because even though this is moving faster, this and this are moving at the same rate. So it's going to all move straight. So in the middle, there is no curl. And so that's how we look at curl using vector field lines. Hope that made sense. I hope I said that right. This is why I stick to physics and not math. All right. So what about the actual equation to the curl? I'm going to show you the first way, which is what you learn in vector calculus. And then there's another way. I don't know if you actually learn it in linear algebra, multivariable calculus, but we'll do it anyways just to see it. So the first is the easy definition of curl, which is defined as this. Let's do it with the curl of B because we're talking about physics here. So the curl of B, and this is actually a vector too, and this should be a cross. So when you take the curl of some vector here, you get a vector back. Whereas when you take the dot product or the divergence, you get a scalar quantity. Here you're going to get a vector quantity, which means it has an x, y, and z component to it. So how do we write this? Well, we would have the x hat, the y hat, and the z hat. I don't know. Sometimes I like writing x hat, y hat, z hat, and sometimes it's I, j, k. It's all the same thing as long as you know that these are some directions associated with them. Now this del operator is a differential in multiple variables. So for the first one, it's going to be d dx. This is going to be d dy. And this is going to be d dz. And then over here, we're going to put the b terms. So there'll be a component in the x direction, a component in the y direction, a component in the z direction. And then we take the matrices of this, or the determinant of this. So just really quickly, there's two ways to do this. One way is to just rewrite this column and this column over again and then do the diagonals. You add them and then subtract the diagonals going backwards. That's one way to find the determinant. The other way to find the determinant is to, let's say we start with x. You hold this side and this term down, and you take the determinant of these four blocks right here. So in the x hat direction, you are going to get d bz over dy minus d by over dz. And what's fun about this is pretty easy. Once you have this, then it's just this thing backwards. So that's the x hat component. And now when you take the y component, this is why I hate doing it this way, but you got to remember that you have to alternate the signs. So x is positive, the y is negative, the z is positive again. So we're going to do minus the y component term, and that's going to equal, now you hold everything in the y line down, and it's going to be this term and this term. And you do the determinant. So it'll be d and this. So it'll be d bz over dx minus dbx over dz. And then finally, we add to it the z component, and that's going to equal this determinant right here, which is dy dx, dby dx minus dbx over dy. And so that is mathematically written out. And so what this is telling us is that there could be, it doesn't mean that there could be an x component, a y component, and a z component. Typically from the right-hand rule, you know this, and we've kind of been doing this sort of, is we've actually seen what that would look like when you have a current going in this direction right here. This is the y direction. Then there's going to be magnetic field that's moving this way and into and out of the page. So current's going this way, magnetic field's going in and out. We're using the right-hand rule. That's just the curl. Okay. And then this is also the right-hand rule right here. So gradient cross B gives you a third vector going in some direction this way. And then you can manipulate what your coordinates are. So you can rotate your coordinates like this, whatever. But the thumb or the middle finger, whichever one you're going to interpret it as, is going to be the direction of the curl. So that's that. We're not interested in this one. Because we're looking at a cylinder, we're going to use the cylindrical coordinates of the divergence. So the cylindrical coordinates of the divergence is written like this. Let's see here. How am I going to write this? So del cross B is going to equal. Now, here we're going to have some weird stuff going on here. 1 over r in the r hat direction. We're actually putting a scalar multiplied by some direction. That's just how it goes. Then we have the theta component. And then we're also going to have 1 over r in the z hat direction. So that's your direction column right there, or row. And then we do the same thing we do with the divergence here. So it's going to be d with respect to r now, d with respect to theta, and then d with respect to z. So that's the partial derivative. And then over here on this side right here, we're going to have to put it in cylindrical coordinates. So this is going to be b as a function of r. Then it's going to be r multiplied by b as a function of theta. And finally, we have b as a function of z. So that is what cylindrical coordinates of a curl vector looks like. This is, and then you can just change b to whatever vector you want, but this is the rule for cylindrical coordinates here. So what does that look like when we work out actually work out this determinant? Because we're going to use it. It'll be 1 over r in the r hat direction. And then on the inside, we are going to put this cross that. So it's going to be, do I have it? I'll just work it out. D bz over d theta minus u d rb theta divided by dz. So that's this subtracted by that in that direction. And we're going to subtract from it because we got to do the next term right there. This is theta hat. And that's going to equal dbz over dr, dbz over dr minus dbr divided by dz. And then finally, we add to it the last term, which is 1 over r in the z hat direction. And that's going to equal this drb theta divided by dr minus this term right here, which is dbr divided by d theta. And that is the equation in cylindrical coordinates. What's going to be nice about this is it's all long here, but 2 of the components are going to be constant, so they'll go away, and you'll be left with just one directional vector. So it'll make things look really nice. This is the system that we're going to be using when we talk about Ampere's loop. because it's already in a cylindrical form. Now there is another cross product determinant, and that's with cylindrical coordinates, but we don't talk anymore about that. We don't need that. So it doesn't show up, so I'm not going to talk about that. But there is a cross product with spherical coordinates instead. Here's the cylindrical one. Did they teach you this, by the way, in multivariable calculus, this part right here? Out of curiosity? Let's see. Oh, okay. So that's something new. Perfect. Sean says, not too sure. So that means Sean didn't learn it. But that's okay. That's neither here nor there. But there it is. I'm going to come back to it, so I didn't erase it on purpose. Let's look at an example. We're going to do the easiest one just as a sphere. So not sphere. We have our wire here. And I just want to know what the magnetic field is going to be. Woo. Some distance here, little r, and I want to know what the magnetic field, or I want to know what the value here would be if we did the curl for some magnetic field here. Okay, and so if you remember from Ampere's law, we can derive what the magnetic field B is actually equal to using the integral form. So B on the inside is equal to mu naught I times little r divided by 2 pi r, big R, squared. And this is going to be dependent on the theta angle. So it doesn't matter if I put the B here, 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 here. The Z component doesn't matter. I'm looking at it at this specific R, so that's not changing either. The only thing that's changing in this loop is the direction of the magnetic field. So this is B inside as a function of theta hat. Okay? So when we use the cylindrical coordinates on this, what do we get? Let's plug it in and see what happens. Over here, there is no R component to it that we're interested in. There is no Z component. Sorry, I meant cylindrical. Let's see what here. Sometimes to work in spherical, we would say. Yeah, so with that, we call that, what is it, parameterizing or reparameter, changing your variables to go from X. I think it's X, Y, Z to R, comma, R sine theta, comma, R squared sine phi or cosine. I don't remember the spherical coordinate system, how you do the transformation, but it's something like that. I remember in polar coordinates from going from two-dimensional to two-dimensional. So here's what we got. And I'm going to plug it into this equation here. Whoa, that got erased. dr. So over here, if we're going to use this equation right here and plug it into here, what's going to happen is there is going to be no that component. There's going to be no Z component. And it's only going to depend on B as a function of theta. And B as a function of theta is what we have written right here. So I'm going to replace that part right here with parentheses. Should I make it a little bit easier? Let's make it a little bit easier. All of this is a constant anyways. So I'm going to put mu naught I over 2 pi r as C. And that'll be r in the theta hat direction. So C is defined as mu naught I over 2 pi big R squared. All of that is a constant. So we'll call it a constant. So I'm going to, B inside is really B as a function of theta. I'm going to take this and substitute it into here. And we get C times R as my component over there. And then from here, we can evaluate this integral once I get my eraser. So let's do that. Not integral, take the determinant of this. So what are we going to get here? Let's see here. Hey, Helen. So if we take the determinant of this, it's going to be 1 over r in the r hat direction multiplied by, okay, so I wrote theta here. That should be 0. The derivative with respect to 0, the derivative with respect to 0 is 0 minus, now if I take the derivative of this term right here, it's with respect to z. There's no z here. So when you take the derivative of something and there's no z, it's a constant. The derivative with respect to this, with respect to z of this is going to be 0. So the first term, the first part of the vector is just 0. And then we're going to do minus the second term, minus theta hat. And now we're going to take the determinant of this times that. So the derivative with 0 is 0 minus the derivative of z with respect to that is 0. So the second term is also 0. Okay, so far so good. The last part, we have to add to it the 1 over r times z hat, 1 over r in the z hat direction. And that's going to equal, now we have to take this. Well, this one we can do. So r times r is r squared. It's going to be d parentheses cr squared divided by dr minus, so that's that term. And then we take this side right here, that's 0. And look at that. That's why cylindrical components, or the cylindrical version of the determinant, is so nice. This term goes away, this term goes away, and you're just left with this in the z hat direction. So I'm going to work that out. Where do we want to work that out? Let's work it out on this page over here. I'm going to erase that. Okay, so the only term we're interested in is that bottom term. And so taking the derivative with respect to r squared, the c is a constant, it comes out of the integral. We're going to get 1 over r in the z hat direction. And then the derivative of this is going to be c times 2r. Right? You take the c out, and the derivative of r squared is 2r. So there's that. And this cleans up to be equal to, I'm missing something here, aren't I? No, I'm not. The r's cancel out, and we're left with is equal to 2 times c in the z hat direction. Now, what was c? C, I said before, was equal to mu naught I over 2 pi r squared. I believe that's what I said. Yeah. So substituting for c, we are going to get 2 times mu naught I over 2 pi big R squared in the z hat direction. The 2 and the 2 cancel out, and you get mu naught I over 2 pi big R squared in the z hat direction. And this is kind of useful here. What this is saying is that this cross this, which could be in the xy plane, is going, or in the rz plane, or in the r theta plane, will give you something that's perpendicular to both the r and the theta plane, which is the z component right there. So that's what we get there. Now, let's see, we're not finished yet. Let's see if this actually means anything. I divided by, whoops, I put the 2 there. That shouldn't be there. I divided by pi r squared. Well, pi r squared is the area. So if you do I divided by pi r squared, that's equal to the current density. So you get mu naught times J. So B del cross B gives you mu naught times J. And that's what the definition of the curl was. So by doing this out, we end up with what we said that we should get. Okay? So there's that. I'm going to erase the other board. Man, it is finally getting hot today. Oh, actually, before I continue, there's just one more problem we have to do. But before that, I got to tell you something sad that happened yesterday. Or I guess hilarious from your point of view. Well, we'll see. So yesterday, I was low on food. So I went to the grocery store to get some food, right? I don't know if I should tell you the story. I'm so dumb. So I go to the grocery store. This is around 5 o'clock. I get all the stuff that I want. I had to get some salads, some avocados, and then all this other stuff that I bought. And I've got my whole cart there. And I don't know if you guys in your store have the the self-checkout registers where you check out everything, right? So I'm checking out all this food right here. And I finally have everything ready. And it tells me how much I have to pay. I'm like, okay, so I'm going to go pay it. So I reach into my pocket and I had forgotten my wallet at home. Whew. So I've never has that ever happened before. And so I know. I felt so stupid. And I was like, oh no. And then the grocery store is about a 7-minute drive from where I live. But I had some like frozen vegetables, as well as like the frozen fruits that I make for smoothies in my thing. So I was like, I can't leave it there because it's going to be 6 minutes and then 6 minutes back. So what am I going to do? I talked to one of the people in the front and I had to make up some excuse. So I had to make up some excuse. I was like, listen, can we just clear the thing on what I have on the register here? Because I still want to order some more stuff. And she's like, oh, okay. So she clears everything away. And I'm like, oh, thank God. So then I put back everything that I got. Literally, I went through the entire store and I put back everything that I had picked up, put everything in the frozen section back. I did everything because I didn't want somebody else to do it. And I felt so stupid. And then I left with my 2 little recyclable bags that I bring with me. I went home with nothing. I felt so dumb. That was the worst. It's like when somebody makes you put back everything that's not yours. Technically, like I would have paid for it, but I didn't have my wallet on me. I should do like put my wallet, what is it, like the Q code for your phone where you can just tap your phone to use your credit card. But I don't know, man. That was really embarrassing. That was So after this, I have to go to the grocery store again, is the short gist of the point here. Then did you have to go? I'm not going back that same day. My pride has been tarnished, Zoe, for that day. So I was like, I can't go back. I would. So I didn't get the food yesterday. I still had some food at home that I just like mixed together and made. I still had enough food for like a day. So I wasn't like out, but I made tuna casserole, so it wasn't so bad. But still, like that was embarrassing. So when you do go to the grocery store, make sure to not forget your wallet. It's a kind of an important thing. Who would have thought? It's like a kid being told to put back all the candy that they just, like when you're a kid and you grab some stuff and then your mom's like, we're not getting that, put that back. And you have to put it all back. You're like, oh, that's what it felt like. But for somebody that is in his early 30s. Okay, so now that you know the sad stories of my life, let's carry on. So our equation is equal to mu naught times the current density J plus this additional term, epsilon naught mu naught times the change in the magnetic field over dt. So this is the way we write it. This is the way we write it in differential form. What we're going to now do is look at this term right here. So let's not worry about this term. Let's worry about what's happening here. What's going on there anyways? Let's use a different color. Let's use black. So what I'm going to do is I'm going to create a parallel plate here. So we got a parallel plate, and we can say there's positive charge on this plate. There's negative charge on this plate right here, which implies that there has to be an electric field going down in that direction there. And if you have an electric field here, you must have a potential difference between the two plates. So we have a potential difference V between the two plates, and the two plates are going to be a distance d apart. Okay? Now, as is, if we have steady state current, nothing. This doesn't apply for steady state current. But imagine if you had more positive charge coming in, like over time. That would change the electric field. And if you get a change in electric field, according to what this is saying right here, you will produce a current that's going around a magnetic field that is going around this electric field. It's not real, but it's there. So what's going to happen is we create a magnetic field only if we don't have E anymore. We have delta E. So if there's a change in the electric field, we will produce a current, magnetic field, using the right-hand rule. Since the electric field is this way, the current would be going in that direction like that, or the magnetic field. How am I going to draw that? It's going to be kind of hard. Let's redraw it over here. So I'm going to zoom into that picture right there. Here's our field lines. They're changing field lines. And if we have changing field lines, we will produce a magnetic field around those changing field lines, B. Yeah, in that direction right there. So that's what will happen. Okay, that's the idea there. That's where we're starting with. Now, how does that work? This is called the displacement current, by the way. So this is a parallel plate capacitor. A parallel plate capacitor has an equation. C is equal to epsilon naught times A divided by D. But we know that there's a voltage, a potential difference here, and voltage can be given by Q divided by C. Now, wait a minute. We know what C is, so I can replace that down here, and we get that the voltage is going to equal QD over epsilon naught. Am I saying that right? Yeah. QD over epsilon naught. So Q times D divided by epsilon naught is the voltage, but we also have that electric field. Now, the electric field equation is given by the magnitude of the electric field, I should say, is given by the voltage divided by the displacement. So the electric field is given by the voltage divided by the distance, the magnitude of it at least. And so the voltage is given by QD over epsilon naught. So when I substitute for V, this term right here, we get Q over epsilon naught times A. Now, why do I want to know the electric field? Because I wrote this wrong. That should be electric field. Magnetic field is the change in electric field. Because I want to do this right here. That's why. I want to take that term right there. So what I'm going to do is I'm going to take the derivative of this. So d partial derivative with respect to time. and I take the partial derivative of this side, and what I'm going to end up with is 1 over epsilon naught times A. Those are constants, and I get dq over dt. And you should know that the change in Q over time is the current. So what we get is I, and I'm going to write it as ID, divided by epsilon naught times A. Now, I times D divided by area, I over A is the current density. So we get 1 over epsilon naught times the current density, J. And this D stands for the displacement current density. So now what we're going to do is we're going to plug it back in, this equation, into here. Whoop. And what we get is the curl of B is equal to mu naught times J plus epsilon naught mu naught multiplied by this term, which is epsilon naught times JD, 1 over epsilon naught times the current density, displacement current density. The epsilon naughts cancel out, and you get the same terms, I guess, in the same whatever. Mu naught J, that's the current in the wire, and this term is going to be mu naught times JD. This is the displacement current density. And we can clean it up a little bit more and just factor out the mu naught, and we get J plus JD. And that's the displacement current term. Okay, so that's everything for today.